Okay, today we are going to finish up our discussion of organic chemistry. We're going to do the second part, and hopefully by this time you get the joke that's on this slide. I'm also going to take some time today to do some review of naming. So you need to have a piece of paper and be in a position where you can stop the tape from time to time in order to see if you can name the compounds before I reveal the answers. Let me make sure that my camera is getting a good picture here. It looks like it is. I'm afraid maybe a little bit off the bottom. There we go. Let's see if that works. One of the difficulties I'm having is that being able to be sure that my camera is pointed in the right direction. Anyway, this slide shows the beginning of the section on alcohols and esters. And alcohol and esters begins a discussion of what is known as substituted organic compounds. Substituted organic compounds are organic compounds that start with an alkane backbone and then have some substitution which leads to the formation of whatever compound we're trying to form. This shows in nature the production of the first of these compounds, known as an alcohol. The alcohol is ethanol. The substitution is a OH for a hydrogen. Notice that this is ethane with an OL suffix. Alcohols are derived from hydrocarbons, and the functional group that's added to the hydrocarbon is the OH group, and this replaces a hydrogen on the alkane. Now, even though the alcohol has an OH group, alcohols do not chemically behave like bases. They are in no way, they should not be considered organic bases, and they in no way behave like bases. This is actually the fermentation of glucose. This is how various alcoholic drinks are obtained, such as wine and beer, where glucose is fermented in the presence of yeast to form ethanol and carbon dioxide. This, as I said, is the way in which most potable ethanol is produced. Potable is a word that means drinkable. Ethanol can also be produced by adding water to ethene. Ethene is over here. This is ethene, two carbons with a double bond. If you add water in the presence of an acid, the double bond is broken and the OH is then attached to the one of the two carbons. Alcohols can also have more than one OH attached. Here we have the two carbon ethane with two OHs, therefore it's called 1,2 ethadiol. 1,2 as opposed to say 2,2, where both OHs would be on a single carbon. And then on the left, or excuse me, on the right, you have 1,2,3 propatriol. So you have three OHs attached. These are also alcohols, just like the other compounds. These are common examples of an alcohol that has more than one OH group. As I said in the beginning of this lecture, the IUPAC name for an alcohol is to take the alkane name and add the suffix OL instead of ANE. So for example, in this pictured compound, you have 5 carbons across, so the alkane name would be propane. Pentane, excuse me. So this is pentanol. However, the OH is not on the end, it's on the second carbon, so you have to designate that by putting a 2 in front of the pentanol. So this would be 2-pentanol. Another way to do this is to put the 2 between the alkane prefix and the OL suffix. This is much less common way in which this is done. So take a look at this compound and see if you can come up with the IUPAC name for this compound. And I'll give you a few seconds to write down your answer. Okay, if you count the longest carbon chain here, 1, 2, 3, 4, 5, or if you count from up here, 1, 2, 3, 4, 5. In either case, it's a pentane. The second carbon here has the OH, it also has a methyl group. So it would be 2-methyl, 2-pentanol, 2-methyl, 2-pentanol, or 2-methyl pentatol, which is much more difficult to say and I don't like it as well. So 2-methyl, 2-pentanol. This is an ether. An ether is a compound that has a functional group OH, so you have this O in the middle of the chain. You have a methyl or ethyl group on one side, you have a methyl or ethyl group on the other side, and the O in the middle. The IUPAC system does not have a specific prefix for ethers. There are 2 ways to name ethers. The first way is to see that the long part, or the long chain, in this case ethane, is the base chain, and then this represents an attachment to the base chain. So this is methoxy, so methoxyethane. Okay. The older or more common way that this used to be named is methyl ethyl ether. When I was in school, that's how we learned to name this, but this is the more modern name, methoxyethane. The group being added is the methoxy group, the ethane being the base. So see if you can think of what the IUPAC name for this would be. Also see if the older name, you could also think of the older name for this. And I'll give you about 15 seconds or so to write it down. If you need to stop the video, that's fine. Okay. Actually, either one of these chains could be the base chain because they're both the same length. So it's going to be ethoxy, ethoxy, ethane, or diethyl ether. Now here's another compound, another ether compound. Let's see if you can name it. Remember from the last lecture that the 3-carbon with the middle carbon is isopropyl, okay? So remember that, or isopropane. So this would be methoxy isopropane. Also, another way to name it is, as I've shown here, 2-methoxypropane. That is the methoxy group. And this is probably the better way to name it. The methoxy group is added to the 2-carbon as opposed to the N-carbon. And so it's 2-methoxypropane, or isopropyl methyl ether. Now, ethers can be produced in several different ways. Probably the most common way to produce an ether is, as shown in this slide, where you bring 2 ethanol molecules together in the presence of sulfuric acid. This causes a separation of a water molecule and the formation of diethyl ether, in this case diethyl ether. Now this is a functional group you'll need to get the name of on its own, because we'll use that name quite a bit. This is called the carbonyl group. Carbonyl group is a carbon with a double bonded O. Now this can occur on the end of a carbon chain or in the middle somewhere in the carbon chain. If it occurs on the end of the carbon chain, it forms what's known as an aldehyde. You've heard of a compound formaldehyde, for example. So that's when this carbonyl group is on the end of the chain, in which case the one open bond bonds to a alkane of some sort, and the other open bond bonds to a hydrogen atom. The ketone, on the other hand, is when this carbonyl group is somewhere in the middle, and on both sides of both open bonds represent a bonding to carbon. So we'll look at some examples of both of these. Aldehydes, by the way, have the suffix Al on the end of their name, and ketones have the suffix ONE on the end of their name. So you have 2 possible functional groups. If it's on the end, you have some alkane chain out here with the double bond OH on the end, one end or the other. That forms the aldehyde. If, on the other hand, you have an alkane chain on one side and alkane on the other side and the carbonyl group somewhere in the middle, then you have the formation of a ketone. As I said, when you name these, you use the alkane name and then substitute ANE. You substitute ANE with AL for an aldehyde, and ONE substituted for ANE for a ketone. So here, for example, you have the underlying chain is a 2-carbon chain with an OH or an O, double bond O, and an H on the end. So this would be, instead of ethane, it would be ethanal, AL, and it's also sometimes called acetaldehyde. On this one, you have the O in the middle, the carbonyl group in the middle, a four-carbon chain here. Now there's really only one. If it's here or if it's here, it's still 2, so you don't have to use the number 2, and you can just call that butanone. If you said 2 butanone, I would not count it wrong. It's 1, 2, 3, 4, so butane, and then ONE as the substitute for ANE. When you write this in a text, you write it here as CHO, and I'll show you some other examples of this later, so that it is, the condensed formula looks like this, CH3CHO, that's an aldehyde. The ketone is written CH3COCH2HCH3, like that. The carbonyl group is polar, and the geometry of the bonds around that central atom, the carbon atom, is trigonal planar. So this means that for the carbon atom, the hybridization is sp2 with an angle of 120 degrees. Oxidation of an alcohol forms a carbonyl group. So if the the OH of the alcohol is somewhere in the middle of the chain, the carbonyl group will be in the middle of the chain somewhere, and you'll form a ketone. Additionally, if the OH group is on the end, then the oxidation will occur on the end, and the carbonyl group will be on the end, and you'll form an aldehyde. So when you oxidize an alcohol, you form a carbonyl group. For molecules A, B, and C, each represents an oxidation or reduction of ethanol. Or, I'm sorry, it's a question, does each represent an oxidation or reduction of ethanol? So you have ethanol on the left, you have A, which is ethane, B, which is ethanal, and C, which is, we haven't talked about the name of it yet, but it's ethanoic acid. If you think about it, A would represent a reduction, and B and C would represent an oxidation. A is reduced, the bond of the oxygen is replaced by a bond to a hydrogen. B is oxidized because the hydrogen is replaced by oxygen. And C is oxidized because two hydrogen bonds are replaced by oxygen. So if you oxidize an alcohol and the OH is on the end, you form an aldehyde. In this case, you start out with propanol, 3-carbon chain, and you end up with propanal. If the OH group is not on the end, but is instead in the middle somewhere, then you form a ketone instead of an aldehyde. And so you start out here with 2-propanol, that is, on this side on the left, the reactant is an alcohol with in the middle it's a 3-carbon chain, so it's propanol, but it's 2-propanol because the OH is in the middle. And the ketone that's formed is propanone, that's P-R-O-P-A-N-O-N-E, propanone. Now another major group of compounds are the carboxylic acids and esters, and this is several naturally occurring carboxylic acids and esters that occur in nature. A carboxylic acid is when the carbonyl group occurs on the end, and then there's a second oxygen-carbon bond on the same carbon. So for example, you have, let's see if I can find one up there. Actually, none of those pictured up there are acids, they're all esters. But what you have is, let me go back and show you, sorry. This is a carboxylic acid right here, CH3C double bond O, so the carbonyl group here, and then you have another oxygen on the end here that's also bonded. An ester contains a carbonyl group and then a second oxygen bonded to the same carbon, but in this case it's not on the end. So for example, you have this double bond oxygen carbonyl group with an oxygen here, or you have this double bond oxygen with the second oxygen, another one double bond oxygen with the second oxygen. And you notice that these all have the suffix ATE. These are all considered salts of the carboxylic acid. Esters are responsible for the odors that are associated with various plants and fruits. So you see up there orange octyl acetate, that is responsible for the orange smell of an orange. Peach benzyl acetate is responsible for the peach smell. Rum propanyl isobutyrate is responsible for the smell of rum, etc., etc., etc. The functional group of the acid is on the left. So the functional group here is the C double bond O, OH. This whole group here, which is circled now. The functional group of the ester is circled here. And you see they're exactly the same, but like the example of aldehyde and ketone, one is on the end forming the acid, the other is in the middle forming the ester. Now, in naming, particularly esters can be somewhat difficult to name, but you'll notice if you take a line and draw it between the oxygen in the chain and the carbon in the chain, then it's counted this way, 1, 2, so it's acetate or ethanoate, and then it's methyl ethanoate. So whichever side the carbonyl group is the ATE suffix, and the other is the methyl or ethyl. These are named exactly like the other compounds we've been talking about. You take ethane and then substitute oic acid for the ANE, so that instead of ethane, this is ethanoic acid, also called acetic acid. You notice that here, this is propane, but it's got oic acid again, so it's propanoic acid. By the way, if you acid plus a base equals a salt plus water, this is going to be sodium propanoate. Here you have if you draw the line here, you have 1, 2, 3 carbons, so that's propane, but it's propanoate. So the reaction of the acid, carboxylic acid, with a base forms the ester salt plus water. Carboxylic acids are not strong acids, they are weak acids, and on the average, they ionize approximately 1%. Carboxylic acids are made by oxidizing an alcohol to an aldehyde and then oxidizing that to a carboxylic acid, as shown in this diagram. Esters are generally prepared by reacting carboxylic acids with alcohols. Here we have acetic acid combining with ethanol to form ethyl acetate and water. And you can see that the water comes off like that, and you have acetic acid becoming acetate, and then the ethyl of the ethanol becoming, or the ethanol becoming the ethyl group. Now the amines and amides are separated by the fact that they contain nitrogen. An amine is a nitrogen that occurs on the end of a chain in general. It generally contains a carbon-nitrogen bond. And what you see here is the filling of 1, 2, and 3 sites with functional groups, so that you have first methylamine, then dimethylamine, then triethylamine. And that's actually how these are named. When you see the carbon-nitrogen bond, you know you have an amine, and then you just look to see which alkyl groups are attached, and you name it that way. The nitrogen has a lone pair of electrons free, and then 3 potential bonded pairs of electrons that will accommodate either hydrogen or some alkyl group. And these are the lone pairs of electrons. As I said, the naming generally adds the suffix -ine to the name. So it can be methylamine, or it can be methamine. Now, when you have ring structures, this looks very much like benzene, except you have a nitrogen in the place of a carbon in the ring. And this is called pyrimidine because it has nitrogen in it. It does resonate in the same way that benzene resonates, as we talked about in the last lecture. Pyrimidine is what's known as a heterocyclic amine. What that means is, heterocyclic means that the ring structure has two different atoms in the ring. So instead of all the groups in the ring being carbon, like with benzene, you have a nitrogen in the ring. So that's what's meant by the term heterocyclic. The fact that it's nitrogen means that it's an amine. So here you have the bonding between a carbon and a nitrogen, making it an amine, and the fact that you have a carbon and a nitrogen in the ring makes it heterocyclic. Amines, like ammonia, are weak bases. The top equation we have seen many times in our acid-base discussions. What you have is the ammonia with a lone pair accepting a proton, forming the ammonium ion, and that makes ammonia a weak base because it accepts a protein. Methylamine on the bottom can similarly accept a proton and become methylammonium ion. Amides contain nitrogen attached to a carbonyl group. So instead of the nitrogen being attached to a carbon, the nitrogen is attached to a carbonyl group. So you have nitrogen here and the carbonyl group here. And then these R's mean that there can be any type of alkyl groups here or just hydrogen. So for example, you could have a methyl here or an ethyl here, etc. This shows that here you have two hydrogens plus one alkyl group. Here you have, again, two hydrogens plus a long alkyl group, and this is given the name hexanamide. If you count that IDE ending is used to name these compounds. Acetamide can also be called ethanamide. I'm not real good at pronouncing these names. This is the carbonyl group beside the nitrogen. Those are bonded together, and that's what forms the amide. There's the nitrogen. Then the name attaches the suffix amide to the base name. So on the left, you have a 2-carbon chain, so it could be etha or ETH, or aceta is a more common name. On the right, you have hexane. You take the E off and substitute amide for that. You produce a amide by reacting an acid with an amine. Amine being a base, a weak base, carboxylic acid being a weak acid. When you react an acid and a base, you strip off a water molecule, and then you form the amide over on this side, and the water comes off on its own. This is something that's mentioned in your book. This shows how the peptide bonds are formed. Amino acids are complex amines with an acid group. So each has an amide side or amino side and an acid side. You recognize this side as being the acid side and this side being the amine side. And this R factor is what differentiates different amino acids from each other. So leucine, isoleucine, valine, etc., are determined by whatever R is. When two of these come together, there's a reaction between the carbonyl group of one and the amine group of another, with the removal of a water molecule and then a peptide bond formation here. And when you have two amino acids in a peptide bond, it's called a dipeptide. If you have a very long chain of amino acids formed this way, then you're forming what's known as a protein, excuse me. Now the rest of our time I'm going to spend reviewing and going over some naming, because that's going to be important as part of the quiz or test as we move forward. These are all the different compounds that we've discussed. Up at the top here, you have the alkane. Well, the alkane is the most fundamental. The alkene is the introduction of a double bond. Its only difference in terms of its name is the ENE instead of ANE. Alkyne, which is the next one down, is the introduction of a triple bond, so that you have YNE in the name. The addition of an OH group is the alcohol with the suffix OL. The introduction of an OAO in the middle of the chain with alkyl groups on either side is the formation of an ether, which is in this diethyl ether or ethoxyethane. The carbonyl group on the end is an aldehyde. Ethanal, AL, is the suffix. The carbonyl group in the middle of a chain is the formation of a ketone. Here it says methyl ethyl ketone. That's actually the old name. The new name for such a compound would be propanone, PROPANONE. The carbonyl group plus another oxygen on the end is the carboxylic acid. Acetic acid is the common name. Ethanoic acid is the more appropriate IUPAC name. The carbonyl plus oxygen that's not on the end, that's in the middle of the chain somewhere, is an ester. It can be ethyl acetate or ethyl ethanoate. The bonding of a nitrogen to a carbon is the amine. So this is ethylamine. And then lastly, the bonding of a nitrogen to a carbonyl group is the formation of an amide. In this case, ethanamide or acetamide. Acetamide is actually the old name or the more common name. If you use a common name, it is not incorrect. So let's do some review exercises. For these review exercises, I have several of these for practice. I would suggest that I'm going to pause for about 15 seconds for each of these. If you need more time, if you don't have a answer, you can pause the tape until you have an answer, and then the answer will be revealed when you start the tape again. So let's take a look at this and answer, why are these two structures not isomers? Well, the simple answer here is the two structures are not isomers because they don't have the same formula. To be an isomer, they have to have the same formula. The one on the left here is an alkene, hexene, which has the formula C6H12, whereas the one on the right is 2-methylpentane, which is C6H14. In order for two compounds to be structural isomers, they have to have the same formula but different structures. So let's take a look at another question. give the IUPAC name for this compound. Okay, for this one you count the longest chain, 1, 2, 3, 4, or 1, 2, 3, 4. Both of those are the same. That makes it butane. There's no substituted groups, so it's butane, A-N-E. And there's a methyl group, and this methyl group, you really don't have to put a number here because if it's on this carbon or on this carbon, it's the same, and if you put it on the end, it becomes pentane. So methyl butane is correct, but if you were to say 2-methyl butane, I would not count it incorrect. All right, give the IUPAC name for this compound. Now this one's a little bit more complicated. Remember that you always start counting on the end where the additional bonding is. Okay, this one's a little more challenging, but if you count 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbons in the longest chain, so that makes it octane. But now it has a triple bond, so that's octyne, Y-N-E. And you would start counting on that side. So this is 1, 2, 3, 4. Now on 4 you have a fluorine and a methyl group. 5, 6, 7, 8. So this would be 4 methyl, 4 fluoro, 1 octyne. 4 methyl, 4 fluoro, 1. That tells you that the triple bond is on the end, octyne. A little bit more challenging. How about this one? Give the IUPAC name for this compound. Interestingly, this compound is the same as one of the other compounds. It was just drawn in a different way. I wanted to see if it would trip you up, and it didn't. 2-butane, 2-methyl butane, or just methyl butane is the correct answer. All right, see if you can give me the IUPAC name for this compound. Okay, again, you begin counting from the end that has the double bond. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is another 8. So octane, but E-N-E instead of A-N-E. Okay, and you have 1, 2, 3, 4 with a methyl group, 5, 6 with a bromine group, 7, 8. So it would be 4 methyl, 6 bromo, 1 octene. 4 methyl, 6 bromo, 1 octene. How about this one? Whoops, the answer's there. So, unfortunately, I forgot to put the animation in, but here's how that name came about. 1, 2, 3, 4, so it's butane. It's got an OH, so it's butanol. Now it could be on the end or in one of the two middle ones. So you have have to say 2-butanol to differentiate the OH being on this carbon or this carbon versus one of the N carbons. So 2-butanol. How about this one? Let's give the IUPAC name for this compound. Okay, let's count. 1, 2, 3, 4, 5. So pentane, but it's an OH, so it's pentanol, OL. And you start counting on this end. 1, 2, so 2 iodine and 2 for that. 3, and they're both there, so it would be 3, 3 dimethyl. So let's start from the beginning again. It's going to be 2 iodo, 3, 3 dimethyl, 2 pentanol. 2 iodo, 3, 3 dimethyl, 2 pentanol. OL because it's an alcohol. In class, if any of these names don't make sense to you, you can ask, why we named it the way we did, and I'll go over it again. Now here's another. See if you can give me the IUPAC name for this. Okay, this is an ether, and the longer chain is the base chain. So this side is the base chain. So butane is the base chain. And this is what's added on. It's 2 carbons, so it's ethoxybutane. The old name of this would be ethyl butyl ether. So the 1 tells you that it's attached to one of the ends as opposed to one of the interior carbon atoms of the butane molecule. So it's 1-ethoxybutane or ethyl butyl ether. Here's another compound. See if you can give me the IUPAC name of this. Okay, the base chain is now propane, 3 carbons. Again, it's on the end, so it's going to be 1-ethoxypropane, or ethyl propyl ether. Now, we talked some about oxidized versus reduced. So here's a review question to see if you understand the difference. And you're supposed to rank these in the order of least oxidized to most oxidized. So take a second and write the letters in order that least to most oxidized. Okay, it's going to be, this contains no oxygen, so it's the least oxidized. This contains 1 hydrogen substituted by an oxygen, so it's second. This contains 2 hydrogens substituted by an oxygen, so it's third. And if we had a carboxylic acid over here, it would be even more oxidized. So it goes from here to here to here, then to carboxylic acid. What would be the oxidation product of this molecule? Okay, you already have a carbonyl group here. And so the only thing you can do to oxidize it more is to add an OH where the H is there. And so you would end up with CH3, CH2, COOH, or propanoic acid. This is propanal. If you oxidize propanal, you get propanoic acid. How about if we did the first oxidation step of this compound? Okay. If you oxidize this, the first oxidation step is to remove that hydrogen and make that a double bond oxygen. And so you would form CH3, CH2, CHO, or an aldehyde, propanal. Now, if you were to reduce the first reduction step of this compound, what would you end up with? Okay, if you substituted one of these bonds with a hydrogen, you would end up with CH3, CHOH, or ethanol. And so the first reduction step for ethanal is ethanol. How about the first reduction step for this compound? Okay. If you substituted one of these double bonds, one of these bonds with an OH, you'd end up with CH3, CHOH, CH3, isopropyl alcohol, or 2-propanol. Okay, let's go back to the idea of isomers to make sure you haven't forgotten. Here you have two compounds. Why are these two compounds not isomers? In this case, these are not structural isomers because they're the same compound. There's no difference if you bend this direction like this, or if you keep it straight like this. They are exactly the same. So they have the same formula, but they also are considered to have the same structure. So that's why they do not have or are not isomers. The bend there is irrelevant. What is the IUPAC name for this compound? Now this one you have to take into account the fact that you have a fixed double bond here, and so that this chlorine can be on this side or on that side, and it's across from this group here. So this is going to be what's called trans. And so you have 1, 2, 3, so that's propene. So you have trans 1-chloropropene. That second one is actually not necessary, because if you put the double bond here, actually it is necessary because it tells you that the chlorine and the double bond are on the same carbon. If you put the double bond on this side, it would be a different compound, and it would then be 1-chloro-2-propene. It would still be trans, by the way. So it's trans 1-chloro-1-propene. Oh, the answer is there. You see that your longest chain is in the middle, even though don't let all these things on the side confuse you. That your longest chain is right here, You start from this end because this is the most complex part. It's 1, 2, 3, 4, 5 pentane, 2, 2, 4 trimethyl pentane. See if you can give the IUPAC name for this compound. Now this one's a little bit more complicated. So the IUPAC name for this is 3-chloro, 3-ethyl, 2-hexanol. There's a answer in the key that says that this is heptanol, but there's no straight chain that's greater than 6 carbons, and the longest straight chain is either 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. But because the OH is over here, you should count this way. So 1, 2, 3, 4, 5, 6. You have 3-chloro, 3-ethyl, 2-hexanol. The answer key, this is in your book, and the answer key in the book is incorrect on this compound. What is the IUPAC name for this compound? This is an ether. The dominant chain or the base chain is on this side, so it's propane. You have a methoxy, and it's on the end, so it's 1-methoxy propane. Also can be called 1 or methyl propyl ether. What is the oxidation product, the first oxidation product of this molecule? Okay, the first oxidation product would be to make a double bond here and lose this hydrogen. You would end up with a 4-carbon ketone. So this would be butanone. So it would be written this way, CH3, CH2, CO, CH3. And it would be butanone. You don't have to put a number in there, but if you said 2-butanone, I wouldn't count it wrong. And here's the last review exercise. The first reduction product for this compound, you're starting out here with an ethanoic acid or acetic acid, and you're going to substitute this oxygen with a hydrogen. So you end up with CH3, CH2O, okay? Or CHO, excuse me. And so you end up with an ethanal, which is, or acetaldehyde. So it's ethanal or acetaldehyde. That's the first reduction product. Okay, so that completes the lecture and finishes our 2 lectures on organic chemistry. I would suggest that you make sure you practice the other things, the naming, because that's going to be very important to what we're doing.